Good afternoon. LIGO-India's Education and Public Outreach Group is proud to present our guest today, Professor Weiss from MIT and the LIGO project. As you know, Professor Weiss has made seminal contributions to the study of cosmic microwave background radiation, as well as to the study of gravitational waves. He played a major role in the development of the COBE satellite, which marked the beginning of precision cosmology in the 1990s. He's a co-founder of the LIGO project, which made the first direct detection of gravitational waves in 2015. His work is widely recognized. Among others, he's the recipient of the 2017 Nobel Prize for Physics for decisive contributions to the LIGO detector and the observation of gravitational waves, which he shared with Kip Thorne and Barry Barish. Professor Weiss, many thanks for joining us today.
Oh, you're quite welcome. I'm delighted to be here. Yeah.
Okay, so since most of our viewers are young students, could we please start from your childhood? You seem to have had an eventful childhood, starting in Europe during the troubled period and then moving to the United States.
Well, I'll tell you a little about it, but I mean, I'm Jewish. I'm half Jewish. My mother was not Jewish. My father was Jewish. That plays a role in what happened in my early life, because you have to remember what was going on in Germany in the 30s, early 30s, late 1920s. Hitler was coming, and so being half Jewish and my father also being a communist, he was the very worst combination you can think of for the Nazis. We had to leave, and we went to Czechoslovakia. And Czechoslovakia was at that time still quite free. But then in 1938, I remember as a little boy going to the mountains in Tatra, the Tatra Mountains in Czechoslovakia. My father had made enough money so we could go on vacation for a week. And I remember going into the foyer of a hotel, and there was a beautiful Gothic looking radio. I don't know, you're probably too young to know about Gothic looking radios, but they looked like little churches. And I remember as a little boy, I was about 6 at the time, I looked in the back of the radio. There were all these glowing tubes and all this wonderful wiring and everything inside. It looked very exciting in that radio. But what was coming out of the front of the radio was terrifying. It was Neville Chamberlain giving the area around Czechoslovakia called the Sudetengebiet, which is the Sudetenland. He was giving it to Hitler to keep Hitler happy. And that was the wrong thing to do, but that's what they did. And so immediately everybody who was in that hotel who had either any connections to being Jewish, any connection to being communist, any connection to being German, raced to Prague, the capital, to try to get out of Czechoslovakia. I mean, it's a real efflux. And so we were part of that. And then we finally made it to the United States in 1939, the January of 1939. That's the early childhood.
And what got you interested in physics and engineering?
You have to know the time. I was about 12 or 13 as the war ended, the Second World War ended. And that was enormously interesting for a little boy like me, because New York City was getting all the junk. That was all the military electronics, all that stuff was coming on the sidewalks of New York City, downtown New York City, Manhattan. And there were capacitors and boxes of tubes and oscilloscopes and all sorts of stuff, that like electronics that came from the military. And you could get it for hardly any money. Sometimes they would give it to you just to take it away. So it was very easy to pick up a very interesting hobby called electronics. And that's what happened to me at about 12 or 13. I got all this junk, and in the United States, we have popular magazines. So a kid can learn about electronics. You don't learn really deeply. You don't learn the mathematics. You don't learn really what's going on, but you learn what I call street electronics. Electronics that allows you to fix radios or to make things, you can build things. And so that was a big deal. And so the big thing that happened to me was that I got very interested. I mean, I like music a lot, and classical music, and so did most of the people who came from Europe. at that time. And so I was able to build in 1990, 1947, 48, a high fidelity system, a high fidelity music system with electronics. And I was very, very lucky that there was a movie theater in Brooklyn, which is one of the boroughs of New York, where the movie theater screen had blown up. And there was a big fire behind the screen, and there were a lot of big loudspeakers, wonderful big loudspeakers you could get by just taking them off the wall if you could do it. And so a friend of mine and I got them, and we got about 4 or 5 large movie loudspeakers. And so then I had built an amplifier for those, and an FM radio, an FM tuner, and I had these wonderful loudspeakers. And so I was able to take the New York Philharmonic, or the thing which was beginning to be on the radio with FM radio, and have people come in and listen to it, and they went completely crazy. They thought they were sitting in the concert hall. You could hear every little thing. And so I had a business as a high school student. I had a business fixing and making hi-fi for people. And I got into trouble with one thing, which again is not a technology that's important anymore, but they used to make records. They were phonograph records. Mm-hmm. And the records they were noisy because they were made with shellac rather than plastic. And so when you listen to music on those, you would get very good, nice sound when the thing was loud and fast. But when it was slow and quiet, all you heard was the record scratch, the scratch for the little needle running around in the groove. And that was a terrifying thing, horrible, horrible thing. And here's where it finally came that I just didn't know enough anymore. I want to make a filter that got rid of that noise. And I couldn't do it. Everything I made was worse than the noise. Mm. So I decided I'd go to college.
How did you get interested in gravity?
What happened is I fell in love with a young woman in Chicago, and eventually she wanted nothing more to do with me. And being brash and not understanding the thing very well, I decided to go out to Chicago and fix this problem. Okay. Well, you don't do that, but that's what an adolescent boy does. And I came back. I had spent almost half a year out there I was still a college student. But I decided this was so important that I spent time out there trying to salvage this love affair, but it didn't work. And so I came back to MIT, and I had, of course, not taken the courses. And I flunked out. I don't know if you want to know. Flunk out means just, the grades were so terrible that they threw me out of school. And that's when I really got into physics, because I looked around for a job. And I ran into a guy who became my altar father, and who was a man who was the most influential person in my life. It was a man named Gerald Zacharias. That's not that you should know who that was, but he ran a laboratory at MIT making atomic clocks. And he was one of the first to do that. And I was his technician. Well, he had a big lab. I was one of the people. I was a union member, card carrying electronics technician. Okay. And so I built all this stuff for him, and we got to be very good friends. And after he built the first atomic clock, and it worked, and that became commercialized. In fact, they're all over the world, those clocks. They were the cesium clock. That was he decided that he wanted to do something that was interesting for science and was important for science with the clocks. And he had the idea that he wanted to do an experiment to show the Einstein redshift, and this is where I first heard about Einstein. First time I ever heard about anything but to do with relativity. The idea was very exciting. It was we were going to do an experiment where he was going to be in the valley of a mountain. I was going to go up on top of the mountain. In fact, we had picked the mountain. It was Jungfrau in Switzerland. And because there's a great big laboratory on the top of the mountain you can bring things to. Mm-hmm. And we were going to take one of these new clocks he was going to make, put one up on top of the mountain, and I was going to run that one. And he was going to be in the valley and run another one. And we were going to send signals to each other and see if we could see the Einstein redshift, which was at that time really very poorly observed. It had been seen in stars, in white dwarf stars, but very badly. That was, I mean, then after that, a lot of people began to see the redshift.
This was before the Pound-Ripka experiment?
Yes. Oh, way before it. Yeah, yeah. In fact, well, it was in, I'll tell you what, it was in 1957, 58, 59. And the Pound-Ripka was in the, with the Mossbauer experiment. Then that was in the 60s. Okay. But the, yeah. And so what happened is we didn't do it. We never could get the clock good enough.
We've heard that your ideas of using light for gravitational wave detection came through a classroom exercise.
Yeah, I mean, I'll tell you what that was. Okay, well, that's a little more of that same story. What happened there was I had started a group, when I came back from Princeton, I had started a group that was going to do gravitation experiments. And I'll tell you what it was. We never succeeded with this, by the way, this experiment. We were going to try to do something that Dirac and Bob Dicke both had thought was quite likely, that the big constant G was variable. And I won't go into all the reasons for that. They weren't wonderful reasons. I think Dirac had crazy reasons, but Bob Dicke had a little better reasons. He invented a scalar field. He reinvented the Nordstrom theory, by the way. That's what he did, and attached it to general relativity. That's the tensor, scalar tensor theory, and Brans-Dicke. Right? Yeah, and so that predicted also, if you started looking at cosmological solutions, that the scalar component would change, and that scalar component was another way of could be represented. That scalar potential could be represented as a change in G. That's the way I came to it. And so I thought when I get back to MIT, that would be a very important thing to do, to try to show that. And it turned out it's not easy. It was a misery. And only many, many years later did people who did radar measurements of planetary positions, were they able to show that G didn't change by more than part in 10 to the 12, part in 10 to the 12 per year, something like that. And what Dicke was thinking and Dirac was thinking was a part in 10 to the 10 per year. I couldn't do it. The idea was a very crazy idea. I don't think I want to go into it. It was much too ambitious for an incoming professor. And it was nutty to do that. But anyway, that was the experiment. So here I am running a group whose name was Cosmology and Gravity. Very pompous title, okay? That was my research group. And so the head of the department says to me, he calls me in and he says, we haven't had a course in general relativity for 20 years, or maybe 25 years, something like that in physics. I want you to give a course in general relativity. Well, I don't know if you have taught your young people that you have to lie occasionally in your life. And I couldn't say I didn't know any general relativity. I mean, here I am running an experimental group, but I didn't know any general relativity. Let's be blunt about it. I knew a lot about the results of experiments, but I never had dared to go near the tensor analysis or anything of that geometric stuff. And so I had a very complicated summer. I had to learn a lot. And it was also, I had to teach the thing in the fall. And I have to be very, very thankful to a bunch of graduate students who knew that I was a phony, but didn't make a complaint about it, okay? Because we learned it together, the graduate students and a few undergraduates. We sat there as I bumbled through this thing, and we figured it out ourselves, but it wasn't just me teaching. It was them saying, no, you don't, this is the way it really is. I mean, so the students were ahead of me on many, many things, okay? And then Weber was starting his experiments. See, the course that I gave was in 1966. And Weber had started his experiments, thinking about the experiments from the Chapel Hill Conference again. Turns out Weber and Wheeler had already started talking to each other before the Chapel Hill Conference. And who was Weber? Weber was an engineer, electrical engineer, who was a microwave spectroscopist. That's what he was. And he got interested in, just like a lot of other people thought, that maybe now was the time because all the new technology that was available, now maybe was the time to apply that technology as an experimenter to gravity. So he was very much like Bob Dickey in that regard. But his idea was to look for gravitational waves. I think actually Wheeler told him that was probably the important problem to work on. I think that's what I think Kip tells me that that's how it happened. And so by the time 1962 was old, Weber had written his own book on general relativity and gravitational waves. So it was a little inter-science book in which he describes how he was going to go detect gravitational waves. And by 66, when I was teaching, he was already talking at physics conferences about these big bars that he had, these large aluminum bars, which were going to get excited by the strain field that propagates in a gravitational wave. And that in his case, he had developed, instead of talking about the strain, he had made it into a tidal force through the Ricci tensor. And that's not important. You can do that, but I thought it was completely crazy because I was now teaching general relativity. They were no longer gravitational forces. They were gone. Everything was geometry. So I thought it was nuts. Okay. And so I couldn't explain that to the students. So I thought over a weekend, how could I possibly explain gravitational waves, what they do? How would you detect them to the students? And that I felt was my obligation because, well, the one person who knew about experiment was me in that course. Okay, I should be the one who should be able to tell them that. And so I came up with this idea, which was, I thought, beautiful because it was so simple and so easy to calculate. It was idea you take put a clock and a laser on one mass over here. Yeah, okay. Yeah, well, all right. Everything is backwards. I have to figure out, never mind. Here, this is that one mass, has a laser and a clock on it, and then you have another mass. Yeah, you know what that did? It made everything backwards. That thing you recommended, and put on another mass over here with nothing on it but a mirror. So you start the laser over here, and you turn it on for a microsecond, and send a pulse down to here. Come back and look at the time it took on the clock. And that separation of these two things was a function of the gravitational wave. Okay. That was the whole idea. I didn't tell them that you couldn't do that experiment. The clocks weren't good enough. Okay. And the laser wasn't good enough. Nothing was good enough. But that is an easy calculation. You can give that calculation to a graduate student or even an undergraduate student in a general relativity course, and they can do the calculation. It's very straightforward calculation. Everything is measured in one location. You don't have to worry about propagating the clock to another place. Everything is in the same place where the measurements are made in exactly the same place where the clock is. So there's no way of screwing up. Okay. And so what happens is that, I gave a very good answer. You could do that. And that's the explanation I gave them, how you make detection of a gravitational wave. But then we went on to cosmology, and it was much more interesting. We forgot about all of that.
Yeah.
Okay. And that was 1966. And by 1969, Weber had done enough of these experiments. He'd had of these bars. He had one in his laboratory at University of Maryland, another one at a golf course that wasn't too far away from there, a couple of miles away in a shack. And then he had another one in Chicago at the Argonne National Laboratory, and he was seeing, typically, according to him, and I knew him in those days, something like 3 or 4 events a day. On when everything was going right, 3 or 4 events, maybe, well, I'm exaggerating, 2 or 3 events per day. And he saw them coincidentally in all 3 of those detectors. And then he wrote a paper, which was not careful enough, I thought. But he could not think of anything else but gravitational waves that would cause that. And so he announced the discovery of gravitational waves in 1969 in that paper. And a little bit later, about half a year later, he also made one further announcement that he thought the sources of these gravitational waves were in the galactic center of our galaxy. And the way he came up with that is that his bar had the bar had a length, and when the bar's length, when you're normal to that, was facing the galactic center, it was more likely to see a pulse. Then when you turned the bar, so it was end to the galactic center, then you didn't see as much because his sensors weren't sensitive to that. So he then said, yeah, most of these pulses are all coming from the galactic center. Well, that caused an unbelievable amount of work. I mean, thank God for physics and the way that people do physics, because that was not such a hopeless experiment. It's not a hopelessly hard experiment to do. Okay. Why getting a bar, putting it in a vacuum system, putting strain gauges on it is most capable experimenters could do that. And so a lot of people in the world, I know at least 10 groups in the world that immediately started doing that experiment because it sounded like a grand, wonderful new field. And to the disappointment of a lot of people, they didn't see anything. And by 1972, I came to the conclusion that was probably right. There was not any of that. I thought maybe because the bars didn't work because I couldn't understand them, but that's wrong. It turns out the bars can make a measurement, but I had that wrong. But so I decided to go look at that idea of that thing with the laser and the clock and the floating mass again. And of course, I realized very quickly that you couldn't do that experiment. So, but it didn't take very long to realize that you could do it if you put up a triangle. Okay, you had a central mass which had the laser on it, or a laser associated with it, and you sent the light, in both in one direction this way and in that direction to two masses, and then timed the light in those two directions, and that took out the problem with the laser. In other words, you didn't have to worry about the bad fact that you couldn't get a laser which was sufficiently frequency set, independent, and that made a huge difference. And that from then on in, I spent the summer of 1971 really sitting in a little room thinking about all the things that could go wrong in that measurement. I made a whole list of all the different noise of things that could screw it up, and I didn't write it up as a thing to put in a journal because I had a philosophy which I got from Gerald Zacharias, which was you don't write an idea up. What you do is you write an experiment that's completed. That's what you write up. But I felt this was enough interesting, so I made it a little, what's called a technical report from my laboratory.
Now that gravitational waves are detected, how would these observations improve our understanding of the universe?
They already do. It's already happened. Let me give you the examples. It's a hard question. It's a hard question, but a lovely question. I think the fact is that you have to recognize something about gravitational waves that make them different than other things in astronomy. The fact is that, yes, they're hard to detect. And I won't ever argue that they are easy to detect. That's not the easiest way to say it is the little tiny amount of strain that you make, that little tiny push on the mirrors you get, compared to the power that's needed to move them by a gravitational wave is unbelievable. In other words, space is very hard to distort. I mean, that should be what's in everybody's mind. Yes, you're measuring this tiny little, horrible, tiny thing, 1,000th the size of a nucleus, and you're very proud of that. But what the energy it took is enormous, much more than anything that you had ever thought about. So that makes the waves, because they interact so poorly, that makes the waves extremely penetrating. In other words, where you can't look into the sun with light. You can barely look into it with infrared light a little bit. You're going to get a little deeper into it with radio waves. If you want to see right through the sun, into the sun, you could use a gravitational wave. And we're going to do that when we finally get to seeing a supernova, for example. We will see exactly what's going on in a place that's completely shrouded to us. So that is the big change. We can see things that electromagnetic waves cannot see because they get scattered. And gravitational waves don't get scattered at all. So in fact, at some point in the history of man, we're going to look all the way back to the beginning of the universe because of that. To me, that's the most exciting prospect for the future. That's 50 years away from now. So what are the interesting things that already come of this? Lots of stuff. Well, the fact that we saw binary black holes, which people sort of guessed maybe, but then we see them as a major component of the universe. Where in the hell do they come from? That's not been answered yet. I mean, I don't know how if you've been following that, but probably you're doing it yourself. There are now 5 or 6 different methods for making these things. You have to decide between them. There might even be some of them primordial.
Yeah.
That would be unbelievable, but they could be.
Yeah.
So, okay, there is already a deep mystery. Love to know more. I think the neutron star story is even a better story in terms of, let's say, ordinary questions that people in astrophysics are asking all the time. In that one experiment of seeing 2 neutron stars, and I'm assuming your students know what a neutron star is. They're stars that weigh the sun and have the size of, let's say, a city, a typical city. So they're enormously dense, and they're made out of nuclear matter. And now those 2 things, they collide. We know every once in a while they collide. In fact, we thought that was the only source we would see for many years. And all of a sudden, we really got surprised by the black holes. Although people like Kip had already predicted that the first thing we would see is black holes. Why? Because he believed in black holes. But a lot of the world didn't believe in black holes, okay? So, anyway, the neutron star thing showed us a couple of things. Because it was also seen by an electromagnetic source, namely a gamma ray telescope in space, we could see that the gravitational wave speed and the speed of light was the same to a part in 10 to the 15. That's an incredible number. In other words, and that's because the 2 waves have been traveling together for 150 million years. They've been following each other as they go along. And they're only different in time by a second or so, if they are different in time. So that we got that automatically, and Einstein guessed at it. I mean, he guessed it was a pretty good guess. Then we found out that something that people had thought maybe, but now it became a little clearer that in the collision of these 2 neutron stars, you make most of the heavy elements heavier than iron in the universe. It looks that way. Now, that's not proved to the extent that I would like, but people thought that would be the mechanism, because you needed a place where you had a lot of neutrons when they collided together. And then certainly a neutron star is a place where there are a lot of neutrons. So, okay, and we're going to learn a hell of a lot more yet. All of this by looking at this thing in completely different methods, some by gravity waves, some by gamma rays, some by all the different wavelengths in the electromagnetic spectrum. I don't think yet with particles. That will come. We'll see the neutrinos from one of these things. That hasn't happened, I don't think yet, but we will.
Yeah.
So anyway, just that those 2 experiences are, the last one is mostly for people who do astronomy. That's an important, very important thing. It's some physics, but the most interesting physics is actually that Einstein seems to be right in the regime when space is really very badly distorted, like what happens when 2 black holes get together. I mean, I've seen pictures of that. It looks like there's a storm in the ocean. When you look at the curvature, and then at that and strong fields and at high velocities. I mean, when these black holes collide with each other, they're going about, maybe a decent fraction of the velocity of light, half the velocity of light, something like that. And that theory still works.
Yeah.
I mean, that's an unbelievable piece of human ingenuity, that this thing that was made up in somebody's head with some data from the outside, yes, but not everything. Yeah. And that should work in the regime. I don't know many theories in physics which work over such a huge dynamic range. I mean, maybe E&M, but I'm not sure that. Yeah. So we are now looking at what is really gravity. Yeah. Now, many people don't give a damn about that. Well, many of us in physics give a big damn about that. And I hope we will learn a lot more, because there's a big gap in our knowledge. Yeah. And that is how to make a quantum theory of gravity, which you're fully aware of. But your students should know that. And it's not a problem you're going to solve by sitting on your tuchus and just thinking about it. You've got to think about it in a deep way.
What is your favorite gravitational ray observation so far?
Oh, I don't know. I'm just happy it worked. I'm happy with all of it. I mean, to me, it's I tell you, I feel not for myself. I would have been evil about this and continued working on anything as long as I was having fun.
What advice would you give to all the young aspiring scientists?
And I'm going to give you an answer for an American kid.
Mhm.
I can't tell you what an answer is for an Indian kid.
Yeah.
Okay. But maybe India is sufficiently the same that you can apply this. It's very straightforward.
Mm.
As a kid, as a boy, a girl, doesn't matter what you are, you begin to develop some skills like computer programming, or like I did with electronics, or something which is technically useful if you're interested in technology, and have that in your bag of tricks as a kid.
Mm.
Okay. And then you go around and find somebody, an adult, that you think is working on something that's interesting. And very sweetly go up to that person and say, you know, I'm interested in what you're doing. And I wonder if I could hang around a little bit and find out if I could work with you in some way. I don't want to get paid. I don't need the money, or even if I did, I wouldn't ask you for it. But do you need somebody who knows how to computer program data or build things in the lab? Okay, I fixed all these things, or I've made things. And you do that at this level of a high school kid. Now, for example, many of the students I've had were working as people on a farm. They fixed the tractors on the farm, or they fixed cars, or they immediately fit into a lab. They knew how to troubleshoot. They didn't have to be told the most elementary things. So they were not only useful, but they were doing something that was useful to others. And so we at MIT, for example, eventually got smart enough that we started a program in colleges now. When a student comes into MIT, and it's probably true now in many, many universities, where you have a little program, which is in a little book or maybe in a place you go to, where faculty who are working on research said, I would mind having an undergraduate in my lab who can help us with this problem or this particular thing. And boy, I would jump at it if I was a student. And what you do is you go and work with them. You work with an adult, and then you find out what the graduate students do. You find out what a person who's actually doing that kind of science, how he or she operates. And you actually may even find people you rather like. And you'll be able to use later on when you get into the point where you need to find somebody who can evaluate you. It might be all useful. You don't want to do that right off. So in other words, this isn't the courses that are so important. In the United States, I tell that to all the kids. Oh, I flunked this. I said, I don't give a damn if you flunked. I flunked out of MIT. Forget about it. No, what's important is that you have learned something that is useful, and where you have been yourself sitting and trying to solve a problem. You don't do it in an artificial situation like in an exam, a real problem. And you work on it and you work on it. And suddenly one morning it suddenly dawns on you, oh my God, yeah, if I did this, it'll work. That is the kind of experience that you want to have as soon as you can. Okay. And I don't know how that works in India. I worry a little bit that it's very rigid in India. I don't know if it is.
It's true. Yeah.
Well, you got to get out of that.
Thank you very much for speaking to us today, Professor Weiss. Thank you.